So we had an introduction to stress concentrations, and we found that they were required for cyclic loading because of the interaction of material properties and geometry, and failure specifically in cyclic loading. We ended by calculating what the amplitude and mean stresses were for a cyclic loading for our part. Right, that kind of looked like this. And it had a cyclic load P that going from 0 to 10,000 pounds, then back to 0. So fully releasing load. And we found out that our mean stress is just the nominal mean stress, right, which was the 39.8 KSI. And the amplitude is where we need to apply the fatigue stress concentration factor. So that was KT times the nominal amplitude, which was 1.78 times 39.8. $70.6 KSI. Okay, so now we have our mean stress and we have our amplitude, and we realized that the maximum stress now is not equal to just a fatigue stress concentration factor times our maximum stress. Rather, it is the mean stress plus that stress amplitude including the fatigue stress concentration factor. So that came out to be 110.4 KSI. Okay. So we will use these now in thinking about cyclic failure, and we have to go back to our modified Goodman regions so that we can see if this thing is going to fail. Just to recap, this has an ultimate strength of 150 KSI and a yield point of 120 KSI. So we are close to the yield point, right? 110 is fairly close to 120. And if we go back to our rules of thumb, I think it was way back like in chapter 7, we can approximate the endurance limit, because this is a ferrous metal, as half of the ultimate strength. So in this case, that's 75 KSI. So our maximum stress at that notch is definitely greater than the endurance limit. So this thing is not expected to have infinite life. So we can, if the question is just, is it expected to have infinite life, yes or no, problem's over here. Right? Because we are stressing it above the endurance limit. And we could even, translate this, right? If we don't usually compare that. So we could apply the Goodman equation and even translate this, right, to what is our sigma n and calculate, and so what is our sigma n? And then how does that relate to the endurance limit? It's also above the endurance limit. Okay, so we do not have infinite life. We do not have 10 to the 6 cycles, so we know n is less than that, our actual lifetime. Okay. So going back to those regions for the modified Goodman diagram, we had regions A and B had a mean stress less than 0. This is not our situation. So we are in C or D. And we have a mean stress that was like 39. Our sigma mean, right, was like 30. Can't keep these numbers in my head. 39.8. So that's fairly low compared to the yield stress and stuff like that. So we are going to be, and you can double check this with the exact specifications, but we're going to be in region C. Okay. So for region C, we had a failure criterion that said failure is predicted in n cycles if we had sigma max minus, and then we had 1 minus R, which is that ratio, times the mean stress, mean, greater than or equal to fatigue strength. And R is that ratio. It's defined as fatigue strength divided by ultimate strength. Okay. So even if, so we know it's not going to last an infinite number of cycles, but let's see, like, what is our factor of safety on that? So that's the first thing that we're going to calculate. So what is our factor of safety if we want an infinite life on like a benchmark of infinite life, right? How far off are we? Okay. And in order to do that, we could say that failure, we could use this failure equation here. Failure is predicted in n cycles. Well, n cycles is now, right, 10 to the 6th, right? If, then this equation is true. So failure would be predicted if sigma max minus 1 minus R, and R is defined there. The strength, the sigma n at infinite life is the endurance limit. So I'm going to plug that in. Let's say endurance limit divided by ultimate strength times our mean stress greater than or equal to the endurance limit. So I've taken sigma n, which is a fatigue strength that you're reading off that SNP plot, and I've just said, okay, well, how far, I want to know how far off we are from infinite life. So my failure in n cycles is going to be at the endurance limit. So I've substituted that in. So I've put, instead of sigma n, I've put in the endurance limit, sigma e. Okay, and now we can rearrange this. So I'm going to say sigma max, and we can put in any number of subscripts here we want to indicate that this is in fatigue, this is infinite life, et cetera, is equal to the endurance limit plus the mean stress times that factor we just had. And we actually defined the endurance limit in terms of the ultimate strength, so that's just 1 minus 1/2. So that's all we put in there. Okay, so let's solve for this maximum stress. So we'll do sigma max, some other subscripts if we want. So we said our endurance limit was half the ultimate strength, 75 KSI, plus the mean stress, 39.8, times 1 minus 75 over 150, which is the same thing as 1/2. So sigma max is equal to 94.9 KSI. Okay, good. Except our real sigma max, I'm going to write real because that's in our loading problem, was 110.4 KSI. So that makes sense, right? So if we wanted infinite life, our maximum stress would have to be limited to 94.9, but it's actually 110.4. So our factor of safety, call it n for infinite life, is equal to what we actually have, or sorry, what we need divided by what we actually have. And we come up with 0.86, so that makes sense. right? We said before, we're not going to get infinite life. Our factor of safety on that is 0.86. Okay, so if we don't have infinite life, how many cycles do we expect this thing to last? If we could assemble, let's say like sort of a SN curve, and then we looked at that, how long would we expect this thing to last? Well, let's look at that in a little bit more detail. There's a nice discussion in the book of this fatigue stress concentration factor, KF. Okay? And you'll recall from just a conceptual understanding that the KF is multiplied times our stress, and then if we are doing a fatigue problem, we're going to compare that, right, in some kind of way to a stress from the SN diagram, right? So that could be like the endurance limit or something like that. Okay, so from a conceptual standpoint, this is how we always think about it. And so in this way, this fatigue stress concentration factor modifies the stress that we actually have in our component. Another way that sometimes this is described is the KF is a strength reduction factor. So let's rearrange this equation. So now, whoops, that should be KF. Too many sigmas going on here. Okay. So we can divide the right side by KF. Now, it's not a factor modifying the stress in our component. It's a factor modifying the allowable stress that we're comparing it to, right? Something from the SN diagram, in this case, maybe endurance limit. So in that case, it's a strength reduction factor. So if you see that notation or something like that, that's the conceptual way that that comes about. And so we're going to use that to modify our endurance limit. And so we're going to draw a different plot along with our sort of mock-up of the initial SN diagram, and then we'll see what this gets us in terms of seeing what the lifetime of this part will be. Okay, so let's draw this SN diagram, just theoretically. We are going to go from, this is in a high cycle regime, so we're going to go from, in this case, this is how the book does it, so that's what we're going to do. We're not going to do like 0.8 or 0.9 times the ultimate strength. We'll just use the ultimate strength. And that's going to be at like 10 to the 0 cycles, one cycle. And then we will draw a straight line out to 10 to the 6 cycles at half of that value, which is the endurance limit. It's not exactly half, but you get the idea, and then we'll draw a straight line from here to here, straight line on a log-log plot, like that. So that's our endurance limit that we were given in the problem. So that's 75, and then up here is 150. Okay, so if we now look at this and we say that we are going to use KF as a strength reduction factor, now we're going to have sort of sigma E divided by KF will be our new endurance limit, right? So our endurance limit before was 75 KSI. Our factor was 1.78. So we can do that. And we come up with something which I did not write down. .13. And this was 75. So this is now our endurance limit, which is modified by by that factor KF. But when we get out to when we get to that super low number of cycles and we're trying to assemble this diagram, our ultimate strength hasn't changed. So we can draw a straight line from the ultimate strength down to that line at 10 to the 6, like that. And that is basically our SN curve, including the notch, right? So that's our SN curve, including the notch. and it's our specific notch with our specific geometry and material properties and loading condition. Okay, so the distance between these two endurance limit lines is our KF. That's what we divided by in order to get that, right? So that's the difference. So that's KF. If you look at now, if we go in lower number of cycles, those lines get closer and closer together, right? So KF here is going to be less than, by definition, is going to be less than the original one that we calculated for any lower number of cycles. So let's take an example, right? Let's go to 10 to the 4. Okay? So if we go and we look at 10 to the 4, and I'm going to use the example plot that I have from the book to come up with these exact values. But on the top line here, it looks like about 93, maybe. 93 KSI, and at 10 to the 4, the bottom line is at 60, hang on one second, let me make sure I got that right. Yeah, that's fine. 80. Okay, so the difference now should be, there should be a lower factor than our 1.78, right? So we could say at that point, KF is 93 divided by 80. I don't have that math either. .16. So it dropped off quite precipitously. And we can do the same thing for 10 to the 5. So if I do that, change colors real quick. 10 to the 5 is here, right? It's going to be something in the middle, and the example problem shows this as KF equals 1.40. So you can see now that it drops to 1, right? If we theoretically take that all the way back to the beginning, fatigue doesn't matter because we've just cycle 1, the thing is broken. But if we get out to 10,000 or 100,000 or 1 million, our infinite life, then that's at the highest number of cycles, we get the highest fatigue concentration factor. All right, does that kind of make sense? Okay. So let's look at, give me one second. If we don't have 10 to the 6 cycles, we don't have infinite life. We have a safety factor on that of like 0.86. Let's take it down 1 decade and guess that our life will be something close to like 10 to the 5th, okay? And then we'll see how close we are with that. So, we have different stress magnitudes now if we have 10 to the 5th life because our fatigue stress concentration factor is different. We have the same mean stress, .39.8 KSI, but now our amplitude is not 1.78 anymore because we're not out at 10 to the 6 cycles. It's 1.4 because we calculated it was 1.4 at 10 to the 5th cycles. That's what we're guessing is our life times the 39.8. So now we come up with 55.7 KSI is our amplitude. And now our maximum is the mean, sigma mean plus the amplitude, So it's 39.8 plus 55.7, 95.5. Okay, good. So in this case, let's apply our failure criterion. And in the past, so we're in region C, modified Goodman. Sorry, handwriting is going downhill here. Okay, region C, modified Goodman. But instead of using infinite life, like we did before, which was 75 KSI, now we're on the fatigue. Now it's a fatigue strength. It's not the limit. So now we actually do have sigma n. And we can go and read that off at 10 to the 5 on our prior chart, and we have 87 KSI now. So let's do the same thing. Let's calculate what is the maximum stress. So I'll write it right here. What is the maximum stress for n equals 10 to the 5 life? Then we'll take our sigma max for really what we have. Hang on one second. Yes. We'll calculate our factor of safety. Hang on, let me just write that equation. Okay, so our n for 10 to the 5th life, right, is going to be well, we actually have, nope, I keep doing this wrong. I keep doing this backward. Factors of safety always get me. Okay. What we actually have, and then our max stress divided by the max stress for 10 to the 5th life. So what is the maximum stress value? And then we'll solve for that factor of safety, the exact same procedure as before. So if we plug all that into the region C, we get sigma max for 10 to the 5th life is equal to now sigma n, which is 87, plus our mean stress, same 39.8. And now we have 1 minus our sigma n, 87, divided by 150. So that's no longer a factor of 1/2 because now that's a fatigue strength, 87. So that's sigma n divided by sigma u, in case you needed that. And that comes out to be 102.9 KSI. Okay, so we're much closer, right? We calculated our actual max as 95.5. And if we had 10 to the 5th, and we hit that exactly, our maximum stress could be 102.9. So we came in a little bit below this time, which means our factor of safety will be greater than 1 instead of less than 1. So our factor of safety on 10 to the 5th is 102.9 divided by 95.5, and it's 1.08. So awesome. So it's close to 1. It's over 1. So we can say that failure happens at approximately 10 to the 5th cycles. Okay. We've taken into consideration non-zero mean stresses, cyclic loading with a notch in axial loading, and we've taken it into consideration correctly. Okay, does that make sense? Yeah? Okay. So now it's going to get a little bit more complicated, Because we're going to add in some torsion into the problem, right? Most rotating shafts have some torsional load on them, and that's how they transmit power. So they have to have that. So it's a very common problem. So now let's use the same cylindrical part with the same geometry of notch. And now we have an axial load, but we also now have a torsional load on this thing. And we are going to assume that the axial loading and the torsional loading occur at the same times. That's going to be critical so that we can apply the right failure criterion. So P is going to be changing in time like that. And our torsional load will also change in time at the exact same frequency. So both of these will hit their maximum at the same time and their minimum at the same time. And that's going to become important when we apply a failure criterion here. So this point in time, I'll just draw a line downward, is our max point in time. The 0 is our min point in time. And our mean will be the arithmetic mean between those two. That describes the situation more generally. And these come into play because we're going to apply what's it called? We're going to be calculating the strain energy density for the failure criterion. Because now not only do we have cyclic loading, but we have a 3D stress state with cyclic loading with a notch, right? So it's kind of like, as I said in the prior lecture, these latter chapters don't introduce a ton of new content, but then implementing that new content on top of what you already know takes some finesse and some really systematic thinking. So that's why we're continuing on with this problem here. Okay, so now the loads are changing. So P, the axial load, is now going to go from 0 to 5,000, because if before we went 0 to 10,000 and it only lasted 10 to the 5 cycles, adding in a torsional load is going to be pretty intense. So it's going to go 0 to 5,000 pounds. And then correspondingly, we're going to add a torque on there, which is going to be releasing as well, and it's going to go up to 400 inch-pounds. Okay, so the overall question says, what would be the safety factor on infinite life design under this more complicated loading condition? So the procedure that we're generally going to follow is we have to think about what is KF for two different types of loading now. That's the first thing we calculate, because that's just a function of our notch sensitivity factor and the geometry, right? So now we have KF, that's what we'll calculate first. And then we'll come in and we'll look at the cyclic loading, and we'll look at the axial stresses induced, sigma x, and we'll look at sort of the max there and the mean and the min. And then we'll also look at the shear stresses induced from the torsion, that maximum value, the mean, and the minimum. And then we will put these together into the multi-axial failure theory for strain energy density. Okay. And then the chapter in which we learned about sort of multi-axial stress states also makes use of the modified Goodman criterion, but when we have multi-axial stress states, we said that we don't know, we can't put it in like region A, B, C, D very easily, because we may have at these different times, we may have different types of mean stresses and things. So what we do is we come up with basically 4 failure criteria. We have to just look at every region. And if we look at every region, we'll choose the most conservative one. That will be the one that we pick. So this is kind of our strategy for working through this. So let's put some numbers on this now. Okay. So the first thing I'm going to do is I'm going to just define my directions. So in this case, we're going to assign a coordinate system such that our axial load gives rise to an axial stress, sigma x. So it's elongated. So the x-axis is along the axis of the beam. And our shear stresses are going to be shear in xy. But let's think about the loading a little bit. So in our part, did our critical location change at all? Right. And so let's think about this notch here. Well, if I have axial loading, then my critical location is everywhere through the cross section, because axial loads are, well, not everywhere through the cross section, where the stress concentration factors are, which is right here, all the way around the circumference. So in axial loading, the critical locations are at the periphery. There are infinite number because if this is a continuous part. So they're at the periphery of the notch, or the periphery in the notch. You know what I mean? Where the red line is. Okay, and so also, let's consider the torsional loading. Right, so we got this thing and we're twisting it and then releasing, twisting and releasing. We know from a lot of past examples that the maximum shear stresses occur at the circumference, and they're going to occur in the notch because that's the smallest diameter. So they also occur at the same location all the way around, right? So the circumference at the notch. And so our critical location is not a single location in this case, but it's a location anywhere on that periphery, but we can treat every location as the same. So it doesn't really matter, but it's somewhere on that circle. Okay, so that's good because we're just going to use the fact that these loads also align in time, and that allows us to use all the criteria that we already know. Okay, so for axial loading, go back, I'll try to keep these colors consistent through here. So KF for the axial loading, we calculated that in the last example problem. So that's 1.78. And we went to the chart and we looked at the chart, we found Q, and then we went forward from there and did KF equals Q times KT minus 1, all that plus 1, and we came out with 1.78. And so now we're going to do the same thing for torsional loading, which is not only a different chart, but also a different curve on the notch sensitivity indexed chart. So I will leave that as an exercise for you if you would like to go and follow the trail on that using all of the things in the textbook. But KF for the torsional loading comes out to be 1.35. Okay. And now we need to calculate these means and amplitudes. So let's do the axial ones first. The axial ones are similar to our other ones, but our maximum load is half. So that means our mean is half. All right, so sigma x mean, we don't have to modify it at all, right? It's just 2,500 pounds divided by our area. So that's 19.9 KSI. Just make sure I do this right. Okay, and then our sigma x amplitude is going to be that same number, but now multiplied times KF because it's a release load. So our amplitude is the same nominal magnitude as our mean. So we'll do 1.78 times 19.9, and we come up with 35.4 KSI. And so we could calculate what our maximum is. And this is the maximum, in time, but also in magnitude. And it's the mean plus the amplitude. So it's 19.9 plus 35.4. This follows the same exact pattern as what we did before. It's just different magnitudes. So we come up with 55.3 KSI, right? Okay, so far so good. Let's do, in parallel, let's do the shear stresses so we don't get too far ahead of ourselves, and we have a multi-axial stress state. Let's go to green. So our tau max now is not just force over area, but we have to do like TR over J. So it's the torque, the mean torque, times the smaller radius divided by the polar moment of inertia using the smaller radius. So we have R equal 0.2 inches. And then we have J is equal to pi d to the 4th divided by 32. And so you can plug those things in. And our mean torque, I think our overall releasing torque, the magnitude was 400. So now our mean is 200, and that's inch-pounds. So that comes out to be a value of 15.92 KSI. We don't have to modify it at all. And now our amplitude is the one we have to modify. So we do the 1.35, which we had from all the charts, times 15.92. And we get 21.49 KSI. And then we can also calculate the max by doing the mean plus the amplitude. And we come out with 37.4 KSI. Okay. So this would be kind of the starting point of some of our prior problems. We would say we have a 3D stress state, we have a cyclic loading, and so we would start here. But now we had to start back and account for the notch first. Now we have arrived here, and we can implement some of the same things that we've been able to implement in prior lectures. Now we have all of these values, so now we can calculate the principal stresses. So the torsion is reversing or is releasing, and the axial loading is releasing at the same period, so it's at the same wavelength, so it's synced up. And so let's calculate our principal stresses where those both are at their maximum. All right, so this is just putting those things into the generalized stress equation and solving for the roots. So now we have, go to like a darker color. So principal stresses at the maximum, where they both have their maximum in time. First one is, I'm going to call it sigma 1 max. Come on, pen. So it's 74.16 KSI. And our sigma 2 max is 0. So yes, it's a 3D stress state, but we can approximate it with a 2D stress state. And sigma 3 max is minus 18.9. So this is like the whole thing with solving the roots or using the Mohr circle. And these are our principal stresses, all at the maximum of their magnitudes. Okay, so we're still in time, but this is the time point where max is now a time where these are at their maximum. We can also look at them at their minimum. Minimum, these are fully releasing, and so these principal stresses go to 0 at their minimum. So sigma 1 minimum is 0, sigma 2 minimum 0, sigma 3 minimum 0, because both of these are fully releasing loads. And then the mean is halfway between those two. So sigma 1 mean, right, instead of 74.16, it's 37.1. Sigma 2 mean, 0, they're all 0. Sigma 3 mean is halfway between 0 and minus 18.9, so it's minus 9.43. So now we have our stress state defined at the point in time where all the loads reach a maximum, all the loads are fully released, and then the mean in between those two. What we then do is we use our distortion energy multi-axial fatigue theory from chapter 7, in which they gave us calculations like this. So UD, this is the maximum strain energy density, right? Max is calculated as a function of all the maximum loads, maximum principal stresses that we just got. So it has a prefactor 1 plus nu divided by 3 times the modulus. And then we do the difference. We do sigma 1 max minus sigma 2 max. Square it, divide by 2. And then we'll add to that the quantity of the difference of the other combinations of principal stresses. So plus, I'm just going to write it out once, sigma 2 max minus sigma 3 max squared, divide the whole thing by 2, and then our last one, 3 max minus sigma 1 max squared, divide by 2, close the bracket. Okay. So we'll calculate what our maximum strain energy density is, and then we'll calculate the mean strain energy density and the minimum based on that suite of values that we just calculated above. And then there are failure criterion as a function of these numbers here, okay? Of how these numbers are combined in the different regions of the modified Goodman. So I'm going to write some numbers on the next slide just as a summary. So the UD max, we're going to leave the prefactor out of this, so I'm just going to write it symbolically. And that comes out to be 7, all the rest of the things combined is 7.25 times 10 to the 9th. UD mean comes out to be the prefactor times 1.18 times 10 to the 9. And our minimum has the same prefactor. Oh, actually, they don't calculate this because it doesn't appear in the failure criterion. Well, it's going to be 0 anyway because all the minimum values were 0. So, okay, there you go. So then we go to the equations back in chapter 7, like 764 through 767. And we apply failure criteria that look like this. So we would say failure is predicted if some, there's a prefactor, so it's the inverse of the other one, which is helpful. That's why we kept it symbolic, to the 1/2 power. And then a bunch of stuff inside some brackets. So UD max to the 1/2 power minus 2 times UD mean to the 1/2 power minus the yield stress greater than or equal to 0. So this is for region A, modified Goodman, and it's multi-axial. And it's the strain energy density, so it's for ductile materials. Okay, so this is similar to what we could do in the past. So we write down for each region. So this is region A. So there's a similar expression with slightly different coefficients and stuff for region B, region C, region D. Okay. So I'm going to make a little chart as to what the results of this are, since we're running a little bit low on time. So for got the 4 regions. So if we plug in all those numbers for our strain energy densities, for the first one, we come out with something that says 0 is greater than or equal to the yield stress. So this is a nonsensical result because our yield stress is always positive. And so this one we can throw out, right? It's just one that doesn't make sense here. For region B, we come up with 42,600, that's PSI, greater than or equal to the endurance limit. Okay, so these are all connected by or, right? Whichever one is the most conservative, this or this or this or this. For region C, we get something similar, except it's a different value. It's 78,480 is greater than or equal to the endurance limit. And then for region D, we get 85,150 is greater than or equal to the yield point. Okay, so we get these kinds of inequalities. So then what do we do with them? Well, we calculate a factor of safety based on infinite life. So we have these values here, like 42.6. And so we calculate a factor of safety based on how this compares to the actual endurance limit for the material that we are starting with. So our factor of safety for this one is, right, what we actually have divided by, nope, I lied. What we, our factor of safety here is going to be the endurance limit divided by what it would be in this failure criterion. So like 42.6. Our endurance limit initially, if we assume infinite life, was 75. So 75 over 42.6 is 1.76. So if we only had that failure criterion, we get infinite life. It's greater than 1. However, if we keep going, for the second region here, let's compare 75 now to 78.48. So you can see now that our denominator is higher. So now we're going to get 0.96. So for that one, we would not get infinite life. And for the final one, our factor of safety, we don't actually have the endurance limit in that one. We just compare with the yield point. So it's the yield point divided by hours, 85.15. Yield point was 120. So we come up with 1.41. So for 2 of them, we do get that we could get infinite life. But we have to choose the most conservative, the smallest number out of all of these to be the driving one, which determines our failure. And so in this case, that is region C, and we have a safety factor of 0.96 against an infinite life kind of criterion. We could go back now. In the prior example, we actually said if our factor of safety is less than 1, then for infinite life, then maybe we could get something like 10 to the 5th cycles, or maybe 5 times 10 to the 5th, maybe 500,000. So we could go back and draw that secondary, modified SN curve, and then try to estimate the life based on this. But our KFs change, and then we have to go through, since KF changes, then all of these numbers change all the way out through the whole thing. So it's very much an iterative process. But if you were asked, okay, I have a notch in a bar that undergoes torsion and axial loading, here's the dimensions, here's the material properties, will it have infinite life? Then you can say, in this case, no, it will not have infinite life based on all of these different considerations. So I think we have like maybe 1 minute for any potential questions. Question here.
Is there a makeup lecture Friday?
There is yes, there should be a makeup lecture tomorrow. Yes. Yep, and that'll be downstairs, room 102 at 3 o'clock. Yep, good question. Okay, thanks everybody.